What happens when you eat food? Glucose is converted to pyruvate in the 10-step process called glycolysis. Pyruvate is then converted to acetyl-CoA, and acetyl-CoA enters the TCA cycle or the Krebs cycle, the intermediates of which produce energy. So we know glycolysis, we know TCA cycle. What happens in between? Pyruvate becomes acetyl-CoA in the presence of pyruvate dehydrogenase. This is what we learned in 11th grade. But unfortunately, this is medical biochemistry and this much is not enough. So this step is what we'll be studying in detail today. Pyruvate dehydrogenase is not an enzyme. It's an enzyme complex comprising of 3 apoenzymes and 5 coenzymes. For those who don't know, apoenzyme is the main protein part of an enzyme, while coenzyme is the dialysable non-protein part. What are the apoenzymes? First is pyruvate dehydrogenase itself, dihydrolipoyl transacetylase, and dihydrolipoyl dehydrogenase. So these are the apoenzymes. They sound like tongue twisters at first, but the more you practice, it will become more intuitive. What are the coenzymes? Thiamine pyrophosphate or TPP. What is TPP? TPP is the coenzyme form of vitamin B1. We have coenzyme A or CoASH, which is coenzyme A with a sulfahydryl group. FAD, which is the coenzyme form of riboflavin or vitamin B2. NAD+, the coenzyme form of vitamin B3. And lastly, lipoamide. Lipoamide is used interchangeably with oxidized lipoic acid. So once again, so that we register, what are the apoenzymes? Pyruvate dehydrogenase, dihydrolipoyl transacetylase, and dihydrolipoyl dehydrogenase. I used to remember this as PDH itself. P for pyruvate, D for dihydrolipoyl, and H, since this is repeating, to stand for dehydrogenase. But if that is counterintuitive, you can remember it however you want. The coenzymes TPP, CoA, FAD, NAD+, and lipoamide. Please note that it is FAD and NAD+, not FADH2 and NADH2. Okay? So what happens? It looks something like this, where there's a lot going on, there's a lot of arrows, but finally pyruvate becomes acetyl-CoA. So this can look intimidating, but let's break it down and let's try to draw this pathway ourselves. We'll start with pyruvate, which we got from glycolysis. What comes to your mind when you look at pyruvate? It is simply a carboxylic acid, COO-. Pyruvic acid is what we are calling pyruvate. Pyruvate, something like this happens, where there's TPP and you get CO2 and hydroxy ethyl TPP. Right off the bat, what is going on? How do you read this double-headed arrow? This is basically, so if this is A, B, C, D, this is a fancy way of saying A plus B gives C plus D. That's all. But you cannot say plus in the truest, chemistry sense. These things might not directly get added. Rather, there can be some kind of substitution or something like that happening. Bottom line is, when you see a double-headed arrow like this, the tail of the arrow represents your substrate and the head represents your products. So pyruvate plus TPP or thiamine pyrophosphate is giving carbon dioxide plus hydroxyethyl TPP. If you want to get more into detail, this CO2 is probably being knocked off and this ethyl part is joining with TPP to yield CO2 and your hydroxyethyl TPP. And if you remember, the first enzyme is pyruvate dehydrogenase. And our first coenzyme is TPP. So one step done, let's move on. Hydroxyethyl TPP becomes TPP again in the presence of oxidized lipoic acid. Oxidized lipoic acid is sometimes just referred to as lipoamide to give acetyl lipoamide. Again, let's not by heart this. You have hydroxyethyl TPP, or in other words, you have something TPP. And in the next step, that something is getting removed. So it's getting transferred to this lipoic acid to give back just TPP. Right? So we've successfully regenerated TPP. Who is catalyzing this step? It is our second enzyme, dihydrolipoyl transacetylase. I'm just writing short form here. Please don't do this in the exam. Write the whole thing. Next, acetyl lipoamide becomes reduced lipoamide. What does that mean? It means the acetyl is being taken by someone else. Who would it be? It would be our CoA and sulfahydryl group. CoA will take the acetyl and become acetyl CoA. Wonderful. This is our final product. So pyruvate, let's go ahead and mark that in, say, purple, and acetyl CoA as well. So we know that this is the substrate and the product. So great. Aren't we done here? Not really. So the thing is, we still have to regenerate as oxidized lipoic acid, and we still have to give chance to our other coenzymes here like FAD and NAD+. So unfortunately this reaction still has to continue. How do we get back oxidized lipoic acid? This reduced lipoic acid should become oxidized, right? And who's going to help with that? It is our good old FAD+. FAD plus will become FADH2. When hydrogen is added to something, it gets reduced. So this is getting reduced while reduced lipoamide is getting oxidized. See, it makes sense. And who's catalyzing this beautiful reaction? It is our third enzyme, dihydrolipoyl dehydrogenase. We're still not done. We have to regenerate FAD+, which means somebody has to get reduced so that FADH2 can get oxidized. So this is oxidized while somebody is reduced. That somebody is our final coenzyme here. It is NAD+. NAD+ will be becoming NADH2. And we're done. At the end of this, we have successfully regenerated all 5 of our coenzymes. Wait, where's the rest? I'll mark these also in. Yes. We've successfully regenerated all 5 coenzymes. We have used all 3 enzymes. And we have converted pyruvate to acetyl CoA, which was the objective of all this. So when written neatly, this is what the pathway looks like. That's it. Now all we have left is energetics. When we say energetics, not just for this, for any pathway for that matter, energetics means the high energy compounds you get at the end of the pathway, which can be used to yield energy in the electron transport chain. I just said energy. So, one may argue that, hey, we have FADH2, so can we use it in energetics? No. And the reason is FADH2 is immediately converted back to FAD+. So, this is not an end product. We can only use the end products that yield energy. And the only end product in this is this guy, NADH2. So at the end of pyruvate dehydrogenase, NADH2 can get oxidized in the electron transport chain to yield 2.5 ATP. This is a standard thing. NADH2 gives 2.5 ATP. That's it. That's it about the energetics. Lastly, let's look at the regulation and significance. How is it regulated? Two ways. First is allosteric modification. Again, I will make a video on allosteric modification if you don't understand it properly. But basically, it just means you have an enzyme, and then you have a substrate, and then you have an inhibitor. The inhibitor does not resemble the substrate. It does not fit into the active site. It fits into some other ectopic site. That's what allosteric modification is. It's very watered down what I just said, so I will make a separate video on that. So regulation, 1 is by allosteric modification, 2 is by covalent modification. People get scared of covalent modification, but let me tell you, it's very simple. Somebody who adds a phosphate group, what would you call them? You would call it a kinase. Somebody who removes phosphate is a phosphorylase. Now, most enzymes are active in the dephosphorylated form, which means pyruvate dehydrogenase with phosphate is SAD, but pyruvate dehydrogenase without phosphate is happy. That's all. So whenever we have too much of PDH activity, it will get regulated by phosphorylating the enzyme. That's what covalent modification means. So we have two types of regulation, allosteric and covalent modification. Now, I swear this is the last thing. Significance. What is the significance of this PDH reaction? We need to understand that this is a completely irreversible process. So pyruvate, which we got from glucose, can become acetyl-CoA. That's what we just did. But acetyl-CoA cannot become pyruvate. Why is this important? If you have learned beta oxidation of fatty acids, you would know that acetyl-CoA is the precursor of fatty acids and fat itself, which means the compound acetyl-CoA represents fat. And pyruvate came from glucose, so that represents carb. So is it possible to get fat from a carbohydrate? Yes. But is it possible to get carb from a fat? It is not. Okay? In other words, there is no net synthesis of glucose from fat. You can make glucose from amino acids, glucogenic amino acids. You can make glucose from pyruvate through gluconeogenesis. But once you go to acetyl-CoA, there is no question of glucose. The fate of this molecule is fat and fat only. Okay? This is the first significance, that it is completely irreversible. Secondly, it is the first, or it is the committed step towards oxidation of glucose, which means glucose to pyruvate, if you know, there are a lot of reversible steps. You can still come back to glucose, but once you go to acetyl-CoA, there's no turning back. That's what they're trying to say. Lastly, let's say somebody has pyruvate dehydrogenase deficiency, or they lack TPP, like an alcoholism or something. Without PDH or without TPP, what happens? You cannot get acetyl-CoA. And without acetyl-CoA, there is no TCA cycle. And without TCA cycle, there is no energy. Right? So they can land up in various problems like Wernicke's encephalopathy or lactic acidosis. How lactic acidosis? Because see, glucose to pyruvate done. pyruvate to acetyl CoA is not happening for some reason. So all of this pyruvate will get anaerobically converted to lactic acid, leading to lactic acidosis, which is a type of metabolic acidosis. So that's it about pyruvate dehydrogenase. I hope this was of some help and I did not just waste around 15 minutes of your time. Thank you.